Okay, so this is the moment of inertia for a rod. So let's imagine that I have, let's take this Lego piece right here. Imagine that it's rotating like this around the center. And I want to calculate the moment of inertia about that. And then I'll do it about the edge where it's rotating about a pivot over here. So the first is going to be this way. Okay. So this has a length of L and a mass of M. And I know the definition of the moment of inertia for point masses is MI/RI squared. So if I break this into individual pieces, I kind of like this. Look at that. Then if I know the mass of each piece and I know the distance for each piece, here's the center. So there, I know these distances to the center like that. Then I can just simply add them all up. So let's take our rod, and I have it centered at the origin along the x-axis, and I'm going to break this into a piece called dm. So now I can find the contribution of the moment of inertia due to this little piece, di, and I'm using d instead of delta because I want to take the limit as the piece size goes to 0 and I get an infinite number of pieces, and that's integration. I'll include an explanation of integration down below. I wrote something and I'll do that. So this is just going to be its mass times its distance from the pivot squared. So this is going to be dm x squared because it has an x value of x. Now I can't integrate this side because x changes and my integration variable is dm. So I need to get dm in terms of dx. So let's consider the length of the whole rod. I know that it has a density, a linear density of m over L. This little piece should have the same linear density. So its length is dm, its mass is dm, and its length is dx. So that means I can solve this for dm, and I get dm equals m over L dx. Now I can put that in here, and I get di equals x squared. I wrote this backwards. M over L dx. Now I can that's just a constant, doesn't really matter. But now I can integrate both sides, and I get I equals m over L. The integral from x equals over here negative L over 2 to here L over 2 of x squared dx. So I don't need to worry about the constant on this side because I have limits of integration on this side. So if I integrate that, I can use the power rule, and I get m over L, the constant, and then I get x, the integral of x squared is going to be x cubed over 3. And then I have the limits from negative L over 2 to L over 2. So I is going to be equal to m over L times, and let's put the 3 there. I brought the 3 out. So I'm going to get x cubed L over 2, and I'm going to cube that. I get L cubed over 8. Right, because I cubed 1/2. I get the 8. And then I'm going to subtract this, but if I cube that, I'm going to get a negative sign. So I'm actually going to add this, plus L cubed over 8. Now I can add these two together, and I get m over 3L. And this is going to be 2L cubed over 8, which is L cubed over 4. So this is going to cancel, and that's going to be 4. This cancels with that, and I get 4 times 3 is 12, so 1/12 ml squared. Okay, what if I want to do this, where I rotate it about this point right there instead? Well, the integral is the same. The only thing difference is now, instead of integrating like that, I shift it like that. So now I'm going from 0 to L. So I get I equals, the integration is the same. I can just skip over here. It's going to be m over 3L x cubed over 3 from 0 to L. So that's going to be, oh wait, I already had that 3 in there. So I get 1/3 m over L times L cubed minus 0. So that's it. And that's the moment of inertia about the middle. And now you'll notice here that this moment of inertia, that's about the end. About this side is much smaller than this. If I rotate, it's harder to change its rotation like this than it is like this. Okay, that's what that says. So, but that's the moment of inertia for a rod. I'm going to do a disc and a hoop in the same video in the next video. And I'm going to do that now. But I'm going to stop first. So I'm stopping.